In today's class, we will learn how to use Simulink to program the board, the Nucleo board that you have available. And we will make some basic examples how to control the LED that is actually on the board and how to read and output other signals and work in Simulink with them. So first of all, let me tell you more details about the Nucleo board, about the actual hardware, so that you have an idea how good the board is, or for what purposes you can actually use it. So this board is using a microprocessor from a family that's called ARM, and it is a 32-bit microcontroller. So internally, the operations are based on 32-bit numbers, and the family of this core is called Cortex-M7. Just to give you an idea, uh, if you see it somewhere in some data file or on the internet, then this is the family. Now the ARM CPU and the Cortex CPU, that's like a more generic family of the microprocessors. So other manufacturers have built also their microcontrollers on this Cortex family or on this ARM family. This microcontroller is called F7F7ZI. This is the specific type of the microcontroller, and this microcontroller has something that's called a floating point unit. Now this means that internally it has hardware to calculate with floating point numbers. So we can use the float type from MATLAB or in C or in Simulink, and you can work with those floating point numbers, let's say, in a natural way in the CPU. Now if this would not have the floating point unit, you could still work with floats in C, but in that case the mathematical operations would be transferred to integers, then they will be performed, and then they will be transferred back to floats. So this means that if you have the floating point unit, your floating operations such as addition, or subtraction, or multiplication, they are much faster than without the floating point unit. Now the speed difference might be something like 100, maybe a little bit more, maybe a little bit less. But there is a huge speed difference if you're using floats and if your hardware actually has the floating point unit, or if it does not have this floating point unit. So this one has them, and we can use natively the floating point operations. Now this 216 megahertz, this is the operating frequency of this microcontroller. You can have it with smaller speed. The trade-off is power consumption. In general, if you run it faster with a higher frequency, then you will have a larger power consumption. So if you are selecting the, let's say, correct or good CPU for your embedded application, then it's always a question of power consumption, which relates to frequency. If you need fast operations, it will have higher power consumption. It is of course the question of price, because a CPU without a floating point unit would be less expensive than the CPU with a floating point unit. And it's of course the question of memory and peripherals that you actually require. Now this CPU has 2 megabytes of flash memory, So in this flash memory we can upload the code and eventually some data, like fixed data I mean. And here this RAM memory is having a capacity of 512 kilobytes. So this is where we can actually store our user data if we need some array or if we need to store some variables, some tables and so on. Now those two peripherals that you see here will be quite important for us because we will be using an analog to digital converter and the digital to analog converter as well. Actually here I see that I have an error. This should be 2-channel DA, not AD. So we have a 2-channel digital to analog converter, which is a resolution of 12 bits, and we actually have an analog to digital converter, which allows us up to 24 channels. And in our examples and also in the semester project that I will assign you next week, then the idea will be that we'll take some analog signal, we'll sample it with the AD converter, we'll make some operation with it on the CPU, and then we'll output the signal as a voltage on the DA converter again. Now of course there are many other peripherals on the board. We will not be using them, just to tell you very briefly what they are. So first of all we'll have digital inputs and outputs. So you can see here that on this part here we have many available pins, and some of them are digital pins, some of them can be configured as DA outputs, some of them can be AD inputs and so on. You can see that here on the bottom we have a USB port. So if you write the firmware for it, or if you download some example, now this microcontroller can be used as USB host. So for example, you can connect a flash drive and you can access the files through this connector on the flash drive, and you can use that as a storage, and you can store your user data, your files, your images, whatever, on this flash drive. We have two buttons here. One button is here in blue, that's the user button. We'll be using it in Simulink as well. And here this is the reset button, so it reset the CPU back to the beginning. Here this part and this connector belongs to the Ethernet connection. We can again connect it to the network, and if you write the software for the CPU by using some libraries, you can send data to the internet, you can read whatever you require. You can use this even as a web server to work with some web pages. You will see today that even in Simulink, many of those peripherals are available as blocks in Simulink. So we'll see that Simulink allows us to access the ADC channels here. It allows us to access the digital inputs and digital outputs. And there are even libraries directly in Simulink for the Ethernet. So if you want to configure the device through the internet, or if you want to store the data that you are actually sampling, you can do this directly in Simulink by using the blocks that are already available. Now let's take a look on how this is actually connected. This is the pinout of the connectors. Now this is not a thing to remember, but it's a thing to keep in mind that such picture exists, and you will need this pinout in order to connect correctly your signals. Now I have placed the document that details this connection also in Moodle. So there is a picture that is showing how these pins are connected, and today we'll use only 3 pins. So let me just select some of them and show you what this description means. So if you look on this board here, now we have different connectors here. We have a connector over there. It has some name. I think it's not visible, but it's I will look on the board that I have in front of me. So this is called CN8. This is called CN11, CN1, and so on. Anyway, you can see it on your board that you have with you. And if you look here, now we can take a look on the connector. This is the CN8 connector. And here they will tell us in the picture where is it actually connected. So this blue stuff that you have on the right and on the very left, now this gives me the pin on the CPU as a name of the port. So the port, there is a port A, port B, and so on, port C. And this, for example, here we can see PCA. So this is port C and bit number 8. And by using this name convention, we can access the pin in Simulink. We can access that also in C if we are using the libraries as we have done 2 weeks ago, if we compile directly the C code. So here, note that those are the names of the pins. For example, here we see pin A, that's port A, and this is pin number 3. And those other symbols tell me what are the alternate functions of my pin. So if I configure it as a PA3, it will be configured as a digital pin. It can be input or output with different configurations. But I can also use any of this alternate function if I configure it properly, and I can use the alternate function. So for example, here we can know that we have A0, A1, A2, and so on. And this is the analog input. So the AD converter in the CPU is connected to those pins. So you cannot choose arbitrarily where this analog converter will be connected, but you need to look in such a picture in the documentation. And if you need, for example, input A0, here you see that it's connected to port A, pin number 3. So if you will be working with the code, you need to know where you should actually connect your wires. So this is the analog input. We'll be using it a little bit later. The other functions, for example, here you can see, okay, now this is the ADC. So this is the analog to digital converter, and here they say it's ADC1 and third input. For example, here we can say, okay, ADC3 pin number 9 or input number 9. So this is again an alternate function telling us where is it actually connected. For example, those yellow blocks are noted as UARTs. UART means Universal Asynchronous Receiver and Transmitter. So this is the serial line that we can use to communicate some data from the board with other devices. We might use it as well because if we will not have access to the labs, which I'm afraid it's still very uncertain, then it may mean that we'll need to use a serial line to transmit the data back and forth between Simulink and between the Nucleo board. So those yellow blocks will be useful for us because we will eventually use them to send some data. And here those blocks shown in magenta, you can see that they say PWM and then some number. PWM stands for pulse width modulation, and this means that this pin can generate hardware-based PWM. So for example, we can use it to control the brightness of an LED. We can use it to control the speed of a DC motor, of an AC motor, and so on. And if we use those pins that have hardware support for PWM, we may use them very efficiently. We just program what parameters should our PWM have, and it will be generated for us by the hardware. So from this picture, you should retain this, where you have an idea about the analog inputs. We may later need it. And from the second page, you should retain the ones highlighted here in red. You can see that here again this is a different connector. You can see many connections, many alternate functions. As I'm saying, it's not a wet thing to remember where everything is, but you should be able to orient yourself in the picture and find whatever you need. Now today we will be using three signals, and we'll be using the signals that are actually connected to LEDs on the board. Now 2 weeks ago we've been blinking with the red LED, which was this one here on the board, and today we'll be blinking with all three LEDs that here are available. Now every LED has a different color. One is red, one is green, and the third I think is blue. So we'll learn how to do this, but today from Simulink. And therefore this is important, this is highlighted. We can see that LED 2 is connected to PB7, which is one digital pin. We can see here that LED 1 is connected to PB0, so it will need to use those pin numbers, so PB0 and PB7. And from 2 weeks ago, we probably remember that the third LED, the red one, was connected to PB14. So the very first example that we will do will be controlling PB14, PB7, and PB0. Those will be the LEDs on the board. Now in order to work from Simulink with the board, you actually need a support package for that. It will add you functions in MATLAB. Now this support package is called like that, Simulink Coder Support Package for STM Microelectronics Nucleo boards. And I actually asked you in chat today in the morning to install this package. Now I hope you have done that, because you will need it, and the installation takes some time. At least on my computer it took like half an hour to install. Now what is it doing is that it will download the compiler and the libraries for the STM boards, and it will install them into Simulink, and it will add additional blocks and additional libraries directly in Simulink. So how you can obtain actually this add-on. Let me now switch to MATLAB, and I will show you how to do it. But I will not install it because I have already made this installation. So if you are in MATLAB like that, you can go to apps, and you can actually take a look on the apps. Here the icon should look like this, add-on, and it should provide us a list of add-ons that are actually available for MATLAB. So just have to find it here on the home tab. Here you see that this is this add-on icons. Now if I launch it, it will search the MATLAB site for the add-ons that are actually available. Now this may take some time, Just try to launch it again, and then we'll see a window saying what is actually available. Now I don't know what's yeah, it's still doing something. So now it's starting to open. Add-on Explorer, and this is basically a repository of the add-ons that you can install in MATLAB. Now some of them are free, some of them are not free, but it depends on your license. You can see that something is already installed in my computer, and here you can see the different add-ons that are actually available. Now you can see that there is really a lot of them. So there is like 40,000 of different add-ons for graphics, for mathematics, for analysis, and so on and so on. So we will be actually searching for the Nucleo boards, which you can see here. And if I just search for the Nucleo boards, it will allow me to install this package. Now you can see that I already have it installed, and I hope that this is also the case for you. Now when I was installing today this add-on, I found that it's necessary that your computer has some free resources. I was doing some scan in the background, and therefore it failed to install and download those components. So if it fails for you, then try it again a little bit later, or wait until your computer is sort of free. Don't compile any videos and so on, and it should install fine. Now you can also do just download the devices, the drivers, and you can install them a little bit later. So if you have some trouble, I have actually downloaded all this installation package. It has about 300 megabytes, I believe, so I can later share it, and it should work also from the offline installation. Sorry?
I have one problem. Because I have one problem because of the add-on. This function is support only the Windows, but I use the MacBook platform. So it's a problem for me
yes.
to install that
And
function.
I don't know how we can actually solve
Yes.
it. But maybe can you install Windows on your computer? It should work.
We'll try.
Okay, so I hope that you all have this toolbox installed. Now let's go to Simulink. Just move here my presentation to a second screen, and we should see this in a library. Now, just in case you have some problems with the board, I have uploaded the driver for the board also in Moodle, because I have found out that on some computers there is a problem that it will not find the board directly. It will not install the driver, so it looks like this, the ST-Link debug without the drivers. So if this is the case, then please take a look in the Moodle folder for the board and download and install these drivers. This has helped for me. Now this year I did not have any problems with the drivers, but I remember that last year with the Czech students, at least in some cases, we had to install this driver because the board was not recognized properly in Windows. I don't know why it's working on some computers and not on some others. So if you have this problem, then you can go to Moodle, and here in the folder for the Nucleo manuals, you can find all the manuals, and here you can find also the driver for Windows, which should work. And the other documents here, for example, this is the schematic of the board, which is in some zip file, and those are the documentation files for the board, for the CPU, and also for some software that we are using in this class. So it should be available here on this tab for you in Moodle. So now what we can do is that we can start creating the code in Simulink. So you need to start Simulink. I already have it started, so I will just open a new Simulink project, and I will show you how to actually configure the board. So just open a new project in Simulink, and when it's open, then we'll start creating the diagram that will control the LED on the board. Now it will look in a similar fashion like you see right now on screen, but I will just create it from scratch so that you can see where do I take the blocks and how do I configure them. For some reason it's taking some time. Maybe I need to close this add-on explorer, and then we should be fine in creating the code. No. Okay, now it's opened. So now we'll create, actually now it opened two, so let me just keep one. Now we will look for the blocks that we have available in the libraries. So I will open the library here, the library browser. I will first drag a signal source to my block diagram, and I want that the LED is blinking. So we'll do basically the same code like we've done 2 weeks ago in C. So I will use pulse generator because this is giving me a rectangular signal. So I will just drag this pulse generator into my block diagram. So this will be my source of the signal, and we will configure this to blink with a certain frequency. So now let me double click the pulse generator, and we will change this setting. We'll keep amplitude 1. Let's change this to period, for example 1 second. So this period will be 1, and the pulse width will be 50% because I want a 50% duty cycle. Now you can change it, you can use different numbers, but this is just what I will use as default. So this is the pulse generator, and now I need the output. So I will connect this output to the pin that's connected to the LED. So if you look here in the blocks, now after you have installed the support package, you see here that we have a new library called Simulink Coder Support Package for STM Microelectronics Nucleo Boards, quite a long name. And here we have the new blocks that were installed. Now we will use today only the ones that are in the common tab here. You can see what is available for us. Now this is the analog input. So this allows me to read the analog voltage from the AD converter from some analog pin, and the output will be some number in float, and then I can do with this signal whatever I want. I can plot it on the chart, I can make a decision based on this voltage, I can for example make a PID controller based on this sample value. Now, we'll not use this, but just to explain you what that is, a CAN is a serial bus that is typically used, for example, in the automotive industry, where the different control units they communicate through the CAN bus, and they transfer what is the position of the accelerator, what is the fuel consumption, and so on. So it's typically CAN bus. It's typically used in the automotive industry, not only automotive, but typically automotive. Now here we have digital read and digital write. That's what we will be using today. We will use digital write because these two blocks they work with the digital inputs and outputs. And we will use right now the digital write because that's giving me zeros or ones connected to the pins, and we will connect the LED to the specific pin number. So let me now just drag this block into the block diagram, and I'll just now go back to this library browser to finish the explanation of those blocks. Here I2C I2C is a serial bus typically used to communicate between integrated circuits. So you can read the data from an accelerometer, from a gyroscope, from a pressure sensor, but the point of I2C is typically that it's on the board and it communicates on short distances, few centimeters, 10 centimeters, 15 centimeters maybe at max. So by configuring those blocks, you can code the program in such a way that it can actually read the data and write the data on this I2C bus. And we'll not be using it here, but maybe with Mr. Hiskey you will be using I2C bus in embedded systems, in C of course. Then this is the PWM output. This is what I was talking about with the pins, and this is quite similar to the digital write block, but there is one difference. If you use the digital write block, it allows you to output 1 or 0. On the other hand, if you use a PWM output, you will configure basically the frequency of the PWM signal and then the duty cycle. So the input to digital write is 1 or 0, but the input to the PWM signal, you can read it here in the help window. Now the input is a number between 0 and 100%, and this gives you a duty cycle. So the output of the PWM pin is still a digital signal. It changes between zeros and ones, but the duty cycle is what you have as information, as the signal. So if you have a 50% duty cycle, now this means that 50% of time it's on logic 1 and 50% of time it's on logic 0. So by this you can control, for example, the brightness of an LED. We'll try it today as well. You can control the speed of a DC motor, and you could use it also for AC motors. Now those two blocks, SCI read and SCI write, they work with the serial line. So through serial line, if you are, for example, familiar with the Arduino board, now this has also a serial line. So here you can send data through the serial line back and forth between the CPU and back. So this is the read function, this is the write function. And we might use those functions in the future if we will not be able to access the labs, and I will actually try to use those functions to communicate with Simulink, with the model of your plant that you will be creating. If we will have access to the labs, we will use this analog signal because this corresponds closer to reality what you see in industrial systems. In industrial systems, it's typically reading the analog input signal. Then your controller is doing something, performing a PID, for example, and then it's creating some signal on the output as an analog signal or as a number or as a digital signal. Now please note that here in those blocks there is no block for analog output. Although the board has this peripheral, in Simulink they did not prepare any analog output block for us. So if we will need it, I have it prepared, and I will post it in Moodle, coded in C, how to actually perform the analog output as well. Those other functions are, well, maybe just out of curiosity, but we will not be using them in this class. SPI stands for Serial Peripheral Interface, and this is also a bus that allows you to communicate with other integrated circuits. So for example, if you have an SD card on your phone or in your camera, for example, then typically SD card communicates through this SPI interface. And if you compare SPI and I2C, then I2C is a 2-wire bus, bidirectional, but the SPI is at least 3-wire bus, where you have 1 wire from the device to your host and another wire from your host to the device, plus some clocking signal. So it has more wires, but it is significantly faster. So for this reason, for example, the SD card in your phone transfers the data through the SPI bus and not through I2C. And the last 4 blocks, if you know a little bit about Ethernet, then this should be familiar. You can see here TCP receive, TCP send, and UDP send. So now this works with the Ethernet interface, and you can send data through the Ethernet interface from the board, and you can read also the data from the Ethernet. So if you configure the blocks correctly, you can send data to the internet. If not, you can locally send them to another computer that's not connected to the internet, but just by using these packets of data here with those functions. So those are the functions that we have available in this Simulink Coder support package. Now let's finish this block diagram. So we just need to configure this pin correctly so that it is connected to the LED. Now for the first example, I will just use one LED on the board. So I will use the red one as we've done 2 weeks ago. So this is the pin PB14, and you need to write it like this because this is a constant saying where is it actually connected. Now if you click this view pin map, it should open us the documentation for the board. See, I just hit apply, and we should see the connections where we can actually connect the pins and where the different peripherals are connected. So this is basically what I just showed you in the PowerPoint. This is where all the peripherals are connected. So if you want to connect a specific peripheral, you need to take a look on this picture, and you need to find it, and you need to see, okay, now I want to use LED number 2. That's how it's called on the board, so I need to use PB_7 and so on. So this is my configuration PB14 for the digital signal. Now I need to connect the signals together like that. So this tells me that the signal from the generator is going into the digital output. Now we need to configure this model so that it will compile and run on our specific board. So you need to go to the modeling tab and we'll take a look on the model settings where we can actually configure for which board do we want the compilation. Now here in this window you can also change the model parameters. So for example here you can change what is the step of your program, what is the solver of obviously in my case now I don't need any solver because there is just a generator and signal. But if you have a model working with for example differential equations, then you may need to select some mathematical solver based on what do you actually want to calculate. Let me change the step size to a fixed step. It's always better to use fixed steps with the real hardware, although here it would work also with the variable step. And the reason why it's important, it's better to use fixed step is that you are sure what is actually your sampling frequency. So choose fixed step, and here I can select what should be my sampling frequency, my sampling time. So let's say it will be 0.01. Now this depends of course on your application, what you actually need, what should be the sampling frequency. But at least if you do it like this, if you select fixed step and some sampling frequency, you know that this is your sampling frequency and that it's not changing. Now we need to go to this code generation tab. Hardware implementation in here. And in hardware implementation, we need to select for which board we will actually be producing the C code. Now, last week, remember that we have produced the C code for the PC. So here we had code generation, we had Intel, probably if you have Intel CPU, and here we have Windows because we are compiling that for Windows. Right now I need to select that I'm using a different board. So here you can see my choices. You may see something a little bit different on your computers because I have installed also other support packages for different devices. So at least you should see this STM Nucleo stuff because this is what belongs to the Simulink support package. And if you want other packages such as the Arduino, for example, you can get them here with hardware support packages. Now you can take a look on the internet what's available. You can have a package for Arduino, for example, for Texas Instruments, and so on and so on. So actually many devices are available for Simulink. Now I will choose this one. This is my board, the Nucleo F767ZI. So I will choose this, and this will specify that the compiler will compile the code for this specific CPU. Now what actually happens in background if you are installing the support package is that it will download the compiler and other necessary software for this type of CPU. So now you can see, okay, switch to the ARM device, which is a different compiler than, for example, Intel. And here, if it's available at this specific family, you could also switch device type. You can see ARM Cortex, that's the CPU that we have. But for example, different CPUs like I don't know which one, but some of them they might have multiple cores. So you may configure for which core you want to upload it, and where do you actually want to run the code in your CPU. So it's quite a powerful tool because it allows you to use a single model that you create in Simulink like that. You can compile it for different hardware, even for your own hardware if you have the compiler, and you can take the C code and you can run it on your device. So let's do it. Now this is sufficient for now. We can of course take a look on the details about the device. Let's take a look just on this table. Here this table is telling me how many bits are actually assigned for different types of variables. So for example, last week we have used floats, so 32 bits, and integers, so in this case it's using 32 bits as well. But I can use also some double type. Here you can see 64 bits and so on. And now this is all fixed, and for this specific device we cannot change that. This is for information how much memory will actually be consumed if you use specific types of variables in the Simulink code. Okay, so now let's just hit OK, and let's see how we can actually run the code in hardware. We can see that it actually now switched to the hardware tab, which wasn't there previously until I did choose that this is a other hardware than a PC. Let me just magnify that, and now the last operation that we need to do is that we need to build the code and deploy it to the board. So now what I actually have in front of me is this board that you should have. You see that my LED is already blinking. I have downloaded the code into the CPU to see if everything is working. Now I will do the same also with you, and we'll see how this is done. So if you want just to download the code and run it standalone on the board, now here we have this button, build, deploy, and start. So I will press it, and now the compiler will start and it will do the compilation of this code. Now this takes some time, I don't know, maybe 1 minute. Here you can see that it's building the code. We can open this diagnostics window where we will see what is it actually doing. So I will comment what is now happening. Now the Simulink is being translated into C code by using the libraries that we had. So there is some C code prepared for the signal generator. There is some C code that is actually prepared for this digital pin block. So now it's taking this code, it's looking how is this connected together. Now you can see that it is accessing some libraries, so that's what we have actually installed. Now you can see that it produced this. It produced some C file, which we could find in the folder, and we could of course edit that a little bit later. Now here, for example, this line that is using some tool chain for the controller. This is telling me that now it started to call in background the compiler for C for this specific microcontroller. Now all this is just let's say the setting of the controller, and now it started to produce the binary files that will be downloaded into the board. And if everything is successful, here you can see, okay, now I have here this binary file, which will now be uploaded to my board. And this board is acting like a flash drive. So if you connect it to the computer, you will see it as a flash drive. And what Simulink is doing is that it actually will copy a binary file to this flash drive. So basically that's happening. That's happening here. And it will, after it's generated the binary code, it will download the code on the, let's call it, flash drive. So now in my case it's a flash drive D. I can find it as a drive in all the drives that I have in my computer. And now this file gets uploaded to the board and it started automatically. So what now happened is that I have downloaded the code to my board. Now you can see that the LED, the red one, is blinking, and this is my code that I have here on well, you don't see it, but the code that I have here created in Simulink. Now let me change the parameters. So for example, I will change the settings of the pulse generator, and I will change, let's say, the frequency of the signal. So here I had period of 1 second, and now let me change it to 5 seconds, so it will be longer, and I'll keep this 50%. So now what should happen is that for 2.5 seconds it should be on, and for 2.5 seconds it should be off. Let me apply that, and let's build it again. Now I hope it's not gonna take that long, but about 1 minute it should take. And after the compilation is finished, we should see that this red LED will blink with a slower frequency. Now this, until the compilation is finished, the old program still runs in the board, and therefore it's blinking with this faster frequency. And when this compilation is finished, we'll see that this stops blinking during the upload, and then it will start blinking with the slower frequency that I have here in the settings of the pulse generator. Now if you compile this for the first time, it will probably take longer to compile because it's compiling all the libraries. When I was trying that this morning, it took like, I don't know, 3 minutes maybe. But then if you are just making changes in your code, it's just compiling what has changed. So now download completed, and you can see, okay, now the LED is blinking with a different. So now let me change this code so that we can actually control more LEDs. Yes?
Excuse me, Professor. After I did every step, after I deployed the code, it showed build error, and I don't have the same result
Okay,
as
show
you
me your
on the
screen
board.
and we'll find out.
Okay.
So I will just move it here. Build procedure for aborted due to error. Okay, you need to scroll up and show me. There should be some line with the error. This is just the settings. A little bit more, maybe. Oh, that's all. Okay. So let's scroll slowly down. So it finished the C code. That's still fine. Building untitled, yes. Okay, scroll down.
Also, the directory is incorrect here.
Okay. Scroll, yeah. It's just the settings, so go down a little bit more. Okay. Show me MATLAB. And the problem might be that you are not in the correct path in MATLAB.
Yeah, this is, I think, the problem in MATLAB. Yeah, this is, I think, the problem
Because
in MATLAB.
what you need to do, I will show you on my screen. So stop sharing, and I'll show you in MATLAB. So now note that here can you see it? Yeah. Here in MATLAB, I'm working on the drive that I call T. And now my current folder is this T directly. So it may be that you are not here in this same path in compiler and in Simulink as well. So in MATLAB, you just need to go to the correct folder like that.
Yeah, I changed it. I changed it.
Yeah, so now it should work.
D for me.
I also discourage you to use spaces in the names, because sometimes it has problems. So for example, if you see this path, then this is like not a good idea, because it has let's say that spaces and check characters and so on. So that's why I'm working right now directly on the T drive and not in any folder. That's most likely the problem. So try it again, and then let me know later if it helped or not. Okay. So now let's modify this code so that we can actually control all three LEDs. So I will just copy this block, and I will copy it 3 times there, like this, and I will just change the pins that I have in my boards. So if you remember from the very beginning, then one was PB14, one was PB7. So I will change this to PB7, and the third one was PB0, and I will use it for the last block. So this will be PB14, PB7, and PB0. By the way, on the board, this PB14 is the red LED. So I'll just enter an annotation here that this is called LD3 on the board, and it's the red one. LD3 red. This is just an annotation. Why is it? Okay, now it's there. The PB7 is called LD2 on the board, and it's the blue one. And this PB0 on the board, they call it LD1, and it's green. So where is this coming from? If I would show you again my pinout for the board, which was here, then you can see that here they call that LED2 on PB7. Here on PB0 they call it LED1, and the other one is not shown here in this picture, but that's the red one on PB7. Now on the board, all the LEDs are this one here on the user LEDs, and you can read the markings on your boards. So now let me just finish this description. So LD1, which was green. This code, this block diagram, is also available in Moodle. So if you want to download it later, you can just go to the Moodle site, and in the Moodle site you can find everything here in this Simulink Coder tab, and here I have uploaded all the examples. So this is the folder for the examples. This is the support package for MATLAB and Simulink. Maybe this is for some older version, so I recommend you to download the new one from the internet. And this is some manuals here for Simulink Coder against some older version, and this might be useful a little bit later when we'll be handling in the lab with the lab card, or if will have the real labs sometime. Okay, so let's just finish this block diagram, and what I will do is that I will insert some logic functions in my circuit, just to show you that I don't need to connect directly my signals like that, but I can have some operations that are actually happening here in this block diagram. So what I will do is that I will insert some logic function, and for example let me use the NOT function, and what this will do is that I will take an inversion of my signal. Now I am searching for the NOT function, but I can find it directly in the Simulink library in the mathematics tab, where I can find mathematic functions. So when this search is finished, then we'll see the NOT function available. Well, let me just search for it manually. I don't know how long this is gonna take. So I will just cancel the search, and I will search for the tabs manually. If now this is possible even to cancel it. Sometimes the computer is doing something and you actually don't know what is it doing. Okay, so now I have interrupted that, so you can see here they have a logic operations, and in logic operations you can see, okay, here logic operator. I will just drag the block in my Simulink, and I will change this function from AND, I will change it to NOT. So it will take the signal from the input, it will do the NOT operation with that, which is a logic operation, and therefore it will have only one input and one output. Now what happens with the NOT operation is that if there will be logic 1 on the input, then the output will be logic 0. If there will be logic 0 on the input, the output will be logic 1. So let's connect it like that. Okay, now it's connected, and I will guide this to the output. So what will happen is that if the red LED will be on, the blue LED will be off. And just to show you that it's really working, then let me drag two nodes here, and I will use these nodes here to control the green LED. So now what I'm actually doing is that I will take the signal from the signal generator, I will invert it here once and invert it here for the second time. So in fact this signal that is going to the green LED will be exactly the same like the signal that is going to the red LED. This is just for the sake of let's say exercise. Of course I could take directly this signal and connect it here and it will be exactly the same. However, what we will see here is that the LEDs will be blinking. They will be blinking with a specific frequency. So let's keep here this setting for 5 and 50%, and we'll just compile our code again. So here we will go to the hardware tab, build and deploy. We'll need to wait until the compilation is finished. I'll just hold my board like this so that we see when it's completed. And what we should see is that the LEDs start to blink. Here they will be over there. Now this is still the old code with the red LED, but when this is finished we should see that the red LED, the blue LED and the green LED will be blinking. So let's just give it a few more seconds to finish, and we should see the result. So now this may take some time, maybe here you see 1 minute for the compile to be finished. If you're more or less more complicated, then it may take a longer time. So now we're in the phase where we already have the C code. Now the C compiler is running, and I don't know, in a few seconds we should see the program to be downloaded in the CPU. Now the red LED will start blinking, and this is my code. You can see now, okay. Now here we have the blue LED, red and green, and you can see that when the red LED is on, then let's just move it like that. Then if the red LED is on, then the blue LED is off. So it's like maybe a traffic light blinking. And here if I have inverted 2 times the signal, then here I can see that the red LED and green LED, they should be on at the same time. You can see it here, the red and the green LED, now it's the blue one, and now it's the red and green one. So this is our code that we have just created in Simulink. Now is this working for you?
Still it's showing error for me.
Okay. I'm thinking how we could solve this. Did you change the folder?
Yes, Professor, I did change the folder. I'm trying now different path. Yes, Professor, I did change the folder. I'm trying now different path. I tried the first directly to the same as you to assign it to the board, but now I'm trying to find the path in my C.
Okay, that might
C hard drive.
that might happen. That might help. I don't know what's the problem. Anyone else was successful in downloading the code?
Mine's working properly.
Okay, great.
Yes, mine's working properly.
How about the others? Let me just call your names and you will tell me if it's working or not. How about Mr. Messas Anes? Are you here, Mr. Messas Anes? Hello? You're not here? Went for a coffee? Okay, so how about Mr. Alam Omar?
Yes, Professor, I'm here. I'm just working with my friend right now. Yes, Professor, I'm here. I'm just working with my friend right now because I have an issue with my license in MATLAB, and I'm still trying to solve it.
And the last one is Ayade Sofilan. So how about your progress? Are you here? I don't know if it's Mr. or Miss Ayade Sofilan. Hello. Not here either. Okay. So I see that I should have 5 or 6 students, but only 3 students are listening. Okay. So it looks like I should take attendance for the class because this starts to get disturbing. Okay, so far we have only 1 successful student that is able to download the code into the board. Okay, so what could we do? You could download the examples from Moodle, and you could try to compile them on the computers. Now there are several examples that you can actually download. Now the one that we were trying right now is this STM Nucleo Blink. This one. It was created with an older version of MATLAB, but it should work in Simulink as well. I did not try, but it should work. What we will now do is that we will modify this example a little bit in such a way that we can actually control the code from Simulink. So what we will do is that we will still be blinking an LED a little bit later. We will run, however, the code now on the STM board, and we'll see in Simulink what is the result. And the code that we will actually try will look like this. Here we'll have a scope that will display the signal as a chart. Here there will be some slider that will allow us to modify the amplitude of my signal. And actually here there is a switch where we can change the signal that we are generating. So for example, here we'll have a square wave, and here we'll have a sine wave. Now both will be sampled. Now what we will do for the first try is that we will do this block diagram in Simulink, and we will run it on the PC to see how it's working, and then we will compile it to the board, and we'll run it on the board. So let's take a look on how this can be done. Now in order to do this, what you actually right now you will not need the board because we'll run it on a PC, but later you will need the board because we'll compile it for the board. So let me just erase this from my block diagram. Now I will keep this signal generator in here because we'll need it for our signal. I'll just move it here so that you can see the libraries, and I will now create a second source of my signal, which will be a sine wave. So let's take this sine wave. I will drag it in there, and we'll need to configure those two blocks to operate in discrete time, so sample based. So if you double click this pulse generator, you can see here that we can use those parameters that we have here in my settings. I will use the amplitude of 1. I will just change the period a little bit. So let's say period will be, let's say, 1 second, and I will keep this duty cycle to be 50% as well. Now I will configure the sine wave. You can see again here what will be the setting. I will keep the amplitude on 1. Now for the time being I will keep the frequency on 1 radian per second, but maybe we will need to change it a little bit later as well. And I will keep the other settings as it is, so phase shift, sample time. Let's just do that this sample time will be TS, and I will define TS in MATLAB. So sample time TS, now we can see now it's giving me an error because now I don't have TS defined, but I can go to MATLAB. I can define that TS equals to something, let's say 0.01 for example, and now I can go back to Simulink. Now the error is gone. If I do it again, TS, and confirm it, now it should be gone. No, what's the problem? Maybe it belongs, the Simulink window belongs to different MATLAB, I don't know. So let me just erase this and create the default value of 0. So it will be sort of continuous function. And now we'll take this. We'll insert a switch. So we need to search for the switch. Now I just need to find it. Where is it? Here it's in signal routing. We will use a manual switch, and the manual switch will just click the switch on screen, and you see like that, double click, and I can change the position of the switch. So right now it will route the signal from the square wave generator like this. It should route from the sine wave. And now we'll just add the gain block, which is in math library. What the gain block is doing is that it takes the input signal and it multiplies that by this number. We can enter the number manually like that, or we could add a slider that will be connected with this gain block. So let me add the slider. We'll keep the gain to 1, and in the library we just need to look for the slider block, and I believe it's called slider gain. So here you can see, okay, slider gain, and just drag the gain like that, and it should allow me to see the actual slider. This is here like that, so you can actually change the parameters within those boundaries like that, from 0 to 2, and change it, for example, to, I don't know, 100. That's just an example. Or the second option, if we use this slider, we may actually drag the slider in Simulink, and we may connect the slider that I just dragged with this slider block, so that we have a variable gain, and we can connect it to the Simulink window. So double click to connect. I will double click that, and double click to connect. Should be this one, slider. And now I can set what is the minimum range and the maximum range. So let's just keep this from 0 to 100, and I can connect now. You can see it selected the gain block, so I can connect them together, apply, and from now on this gain block will refresh, I hope, eventually. Will be connected with this gain block, so that here I will see a slider, and here I will be able to change the values. So yeah, now it is updated. So you can see that now if I will drag this slider, I can see that the number here is changing. So now I just magnified the block, so that now if I move the slider in here to a different position, so for example to now 20, you can see that this is the number that is being used to multiply the signal. So this will take the signal, multiply it with that, and I will output this to a scope. So the last block that we need is the sync, is the scope. That will be the chart that will actually use to plot the numbers that we will see here on the scope. Now, before we run this, there's one more small detail that we should change, and this is this stop time. Now, initially, you can see that the Simulink is running the simulation only to a stop time of 10 seconds. So now if I want to run this continuously until I hit the stop button, I can replace this with the inf, which is the infinite time. So if I run the module, it will run until I hit the stop button. So now let's run this on a PC without compiling. So we'll run in normal mode, and we'll run it here with this button. Now it will run the model. I will see here the result on my scope. I will have to double click when the model is running, And right now what I should see is the sine wave here, because this switch is now here on the sine wave, and therefore I will see the sine wave with my specific amplitude and frequency. So the frequency will stay the same, but I will be able to change the amplitude by changing this this gain on the block. So now my model is running. I can double click my scope here. Let's just wait when it appears. Hopefully it will appear soon. And we should see a sine wave if we actually scale this properly. Well, I will just stop it briefly, and I will first open this scope window somewhere so that we see both on screen. So this is now my model. Let me just arrange it somehow on the screen. So like that. This is my model, and this is my simulation, my chart. I will run it, and here we should see the sine wave running. So if I now scale it like that, you see that this is now a real sine wave. If I now adjust the amplitude in the block, you can see now it has increased the amplitude. Now it's gonna decrease the amplitude like that. So it's acting like a signal generator, and it's producing a sine wave. Now if I double click my my switch, now I have changed that to the square wave generator, which is here, and this is square wave. Again, I can multiply the amplitude like that, and you can see, okay, now it's giving me the same square wave, but multiplied with, so it has a larger amplitude as well. So now we see that this runs successfully on a PC, and now we can run the same code on the board as well. So now let's do it. What I will do is that I will add one more generator, or maybe directly the signal that we have here, and I will connect it to the output pin so that we see that our board is actually alive. So here you can see that the pulse generator has a frequency of period of 1 second, so it's about the same like we had for our very first example. And I will just add the output block here in the commons, and I will use the digital write, and I will add it there, and like that we can interconnect them together. Now what I can maybe try to connect, but it will not work. Well, it looks like it will work, but maybe it will not give us proper results. Here it will work when this signal is square wave, but since this is a digital pin with a sine wave, it will not work properly, because the sine wave has values others than just zeros or ones. So for this reason, I'm gonna just connect this like that, so that we see what is the output signal. It will be the blinking of the LED, and we'll see it on the real board. I will just configure this to the correct pin. So let me use the, I don't know, maybe the red one, PB14. So let's set the red LED. Now what we can do is actually to compile the code. So here everything is set in the hardware. I'll just deploy it to the board like that, and after the compiling is finished, we should see the signal on the real board. So now I just wait when my compiling process is finished. It's always a good idea to have this window open, because here you can see if there is some problem with your code and what is the state of the process. So now let's just wait before this is finished. What will then happen is that on this board now the red LED starts blinking because of this block we have here, and okay, now I have a problem. And the problem is that I have now used continuous time in my block for sine wave. So the problem is here, and we'll have later the same problem here. I forgot to change it. We need to use discrete time. So let's go back to our settings, and let's take a look of on what we actually have available. Now here there will be basically two options. Either for some blocks it's possible to use discrete time versions of those blocks. That's one option. The second option is that we may insert a block that is in discrete here, and that is called zero order hold, and this is like a sampling block that allows you to go from continuous time to discrete time. So let's take a look if this sine wave block allows us to actually change the settings. Sample based, yes, it can. You can see here I can have either time based settings or I can have a sample based settings. So this gives me the option to change from discrete time and to continuous time and back. So now I have changed to sample based. If now I confirm it, now I need the sample time. So that's where my TS comes in. You can't see that. So let me move my video here. So what I've now done is that here I have changed this from time based to sample based, and then here I edit the TS which I have in MATLAB, my constant for the sampling rate. And now you can see that the icon has changed. So now this is a sample based sine wave, not continuous. And I'll do the same here for the pulse generator. Again, I will change it to sample based, and I will add sample time TS, which is a constant that I have in my MATLAB. So apply. Pulse width must be less than or equal to the period of the pulse. So now we can see that it has changed also here the meaning of the numbers. If it is in time based, now period is 1 second and pulse width is 50%. If I change it to sample based, now the period is in number of samples. So let's say this will be 100 samples. What will be the period? And the pulse will be 50 samples. So this will give us the same signal in terms of shape. So 50% duty cycle, 50% time is on, 50% time is off. Again, if I confirm that, now this icon has changed, and we can see it's sample based. We'll just run it on the no, I have pressed the wrong button here. Now it will try to run it on my board, but I did not yet configure the board correctly. So this will compile the code, but it will finish with an error saying that it cannot connect to the board because I did not configure the board properly. Now I need to wait until it fails, and then I will need to go back to simulate. Now we need to wait until it gives me an error, and then I will change it properly. You see that now it's able to compile the code, so it will produce it, but it will not be able to connect to my board. There is no way how this process can be interrupted. So if you make such a mistake like I just did, you need to wait a little bit before it fails. Okay, so it's going to take about a minute to complete the compiling. What I want to achieve is that I want to show you this. We'll see first a similar example here in the computer. Now in this picture, this is a sample-based sine wave. So you can see different samples, and between them there is a straight line because it produces samples only at a specific time interval. Okay, see now it's finished compiling, but now it's trying to connect to my board, but now it will tell me that there is a problem and that it cannot communicate with the board. Now here you can see connecting to target, and since this serial port is now not configured properly, we'll do it a little bit later. Now it will fail like this due to timeout, and now it's saying it cannot connect to my board. So let's go to the settings and run it normally on a PC. So just like that in the simulation tab. So now it will run on the PC, and in here we should see the sample-based chart. Yeah, I will switch it to the sine wave a little bit later, because there we will see that it's really sample-based. In the pulse generator will not be able to see any difference, because this is a square wave signal anyway, so we'll not see any difference here in the chart, in the plot. Now it takes some time on my computer to start actually the model, but now it's not compiling the model. Okay, now there's some problem. Aha, I see what's the problem. If I run it on the PC, I cannot have this block embedded. So what I need to do now is that I will just briefly erase the block, or you could just there is a way to comment the block, but I will just erase it now, I will just run it again, and we will see the sample-based response. And when we know that this actually works on a PC, we'll switch to the development board. So now this is still the rectangular wave. Now I will manually switch to sine wave, and you can see here I could magnify the sine wave. Let me just stop it. Now you can see here, okay, sine wave. Now this is sample based, and in the sample based here we can see that it's really the sine wave is composed from different samples. So here there's some sample here, there's some sample there, some sample there. Now by changing the ratio between the sampling frequency and the number of samples per this period, we can make it a better sine wave. But anyway, it will be sample based. Okay, so let me add back my block for the STM board, the digital write, like that, so that we see that it's actually doing something. So I just need to configure the pin again. So this will be PB14, and let me directly configure this so that we can operate the device from Simulink. So there is one more step that we actually need to do, and that's we need to select the communication port which is used to talk with the hardware. So this board, with respect to the PC, is acting like a flash drive, but it's also acting like a serial line. So if we configure the serial line properly, we may send data back and forth from this board into Simulink. Now if you want to find out the correct serial line, you need to go to the device manager in Windows, and what you will see is something like this. So here I can see different devices, and here in COM ports I can see this line. So it's telling me that STM microelectronics board virtual COM port, in my case it's COM16, and I need to enter this number into Simulink to configure it properly. Now initially it's connected to COM1, which I don't have connected right now on my computer. So that's the reason why it failed in Simulink to communicate with the board. So in my case it will be COM16. In your case it will be most likely some other number. So I will need to remember COM16. Now I need to go back to my configuration of my model. If here you go to model settings, then what you can do is that in the hardware implementation tab we can set the correct COM port. So far we've used the hardware implementation tab only to configure the board, which we have over there. But now if we go to this advanced target hardware resources, we can scroll down, and here we have something that's called an external mode. Now remember that last week we have used the external mode to talk with the code that we have compiled in Simulink. Now it will be the same. We will compile the code and Simulink will talk through the external mode with our board. So here I need to enter COM16, that's in my case. In your case it will be something else, and then this needs to be done properly. We'll keep the other settings such as the baud rate and so on. So now just hit OK. And now I could go back to this hardware tab, and I can run this right now with this monitor and tune button. So I'll do this. It will compile the code, and after the building is finished, we will see the result here on this board. So let me just magnify all this like that. So after this is finished, after about 1 minute, you should see that my LED starts blinking. However, now Simulink will be connected to the board, to the serial line, and I will be able to control the switch that I have here by double clicking on the icon, and here I will see this result on my chart. But now the result will not come from Simulink, but will come from this board. So let's just wait when this is finished, and we should see the result. Now in your computer it may probably be compiling a little bit faster. My computer right now is somewhat busy because I'm recording this screen so that I can post the video for you later. So it's taking a lot of resources on my computer. Okay, we should be about there. Now it's building the code. Should take a few more seconds. Okay, so now it built the code successfully. Now it's trying to communicate with the board. You can see here it's saying connecting to target. Now it's saying 1. So okay, it is now communicating with the board. We should see when it starts a little bit later. Now we should see that the LED will start blinking, and now you can see here this LED over there, the red one is now blinking, and now this Simulink code runs. You can see it over there, how the time is running, and here on the scope, now this signal, that's actually what is coming from the real board. So it's not coming from Simulink like running on the PC, but it is coming from the real board, from this one that is doing the calculations. Now if I switch this switch to the square wave, now again this is a signal that is coming from the board and not from the PC. If now, for example, we would have an analog output in there, we would see that on the oscilloscope that this is producing a signal. Now I have a little bit later the similar example like that, but I will show you only the record on my screen, because now obviously we don't have access to an oscilloscope, or at least you don't have, but I have a few of them in my office. So now we have successfully started the code that runs on the board. We can control the code from Simulink, and this is a simple code. What is it doing? I can of course change the gain here. and by this I will have different amplitude here on my screen. So if I change the scale now, I have something like 42 amplitude, but still this is produced by the CPU, not by the computer. If you want to stop it, here use this stop button, and it will disconnect from the board. Okay, so last two examples that maybe just last one that I will show you just on screen, because in order to show it properly we would need an oscilloscope, which you don't have right now. So just keep watching what I will show you and explain you here on screen. You have those examples again available in Moodle, so you can download them, you can run them, and well, they will run on your board, but you will not see the inputs because you will not have the signal generator and the oscilloscope. So this is for the lab only. So what is it? Here we have a block diagram that is using the analog input block. So this is from the library. I have configured it in such a way that it's using input PA3 for no specific reason at all. I've just chosen PA3 as my input. And now I'm making a decision. This block is a switch, and it will switch between the 0 here that I use as a constant and between my pulse generator. And the point of this compare block is the following. If my input signal is larger than 0.5, again this is just an arbitrary value that I've chosen, then if it is larger than 0.5, it will be here, so it will give me the signal from the pulse generator, and if it's smaller then it will give me 0. So now if I would connect the real signal from the signal generator, for example, and if I adjust the amplitude between 0 and 1, then this output will give me a signal. If my analog signal is above 0.5, it will give me 1, and if it is below 0.5, it will give me 0. So I can use this as a detector to detect if the amplitude of my signal is larger than 0.5. Now what we will see on the output is something like this. It's a rectangular signal that is switching between 0 and 1. And for this specific case that I'm showing in this example, now this signal was going from 0 to 1, so from minimal value to the maximal value. So it had full amplitude, and therefore this output signal has a duty cycle of 50%. Now if it would not go all the way to 1, if it would go, for example, just to 0.8, then obviously the time when it's below 0.5 would be longer than the time it's above 0.5. So this would give me a different duty cycle. So this is what you will see on the scope. Now this block is my LED, it's the red one, and on PB14, and this was used to show me visually on the board that it has detected the signal and that it's either on or off, so that we can see and that the signal is the same on the scope like on the real output. So this is how we can use actually the analog input block. Of course, you can take this number and you can do whatever you want with that. Now if you look in the help for this analog input signal, they tell that it's producing numbers between 0 and 1. So 0 means 0, 1 means full scale. So it's not a voltage in volts, it's not a number between 0 and some power of 2, but this is a ratio compared to the scale of voltage that you can connect to the AD converter. So if, for example, the AD converter on this device can work from 0 to 3.3 volts, then if you get 1, it means 3.3 volts. So if you want real volts here, you need to multiply that with a constant value that you need to calculate in advance. So that's one example that you have available in Moodle. The second example is using the PWM output. And we can actually try this right now on the hardware because we can connect the PWM output to the LED. Again, this example was made in such a way that we had an oscilloscope connected to this pin, and this was what was adjusting the PWM, so that we have seen different pulse width on the signal. But again, without the oscilloscope in the lab, we cannot try it. I have a later here this record that I will explain what it means in the presentation. So let's just do this part of the code with the pulse generator and with the LED. Now I will what I will do is I will change this block diagram slightly, so that we see directly the PWM signal on the LED. So it will not be exactly the same block diagram like in the presentation, but it will be slightly different. So now I will go just here to my block diagram, and I will use it to control the board with the LED. So I will erase the sine wave, I will erase this manual switch, but I will keep the this constant, this gain block, and I will keep the scope as well, so that we see what is actually happening. Now let me drag the PWM output to my block diagram, and I will erase this one as well, because this one controls the pin PB14, but I need a PWM block here, which is basically some other hardware inside. So this is my PB. I will drag it like well, let's see first the help here for this PWM output, because we need to figure out what is the input. So here they say that the input value should be between 0, which produces 0 duty cycle, and 100. So it will be actually a number between 0 and 100. I will first configure this. It will not be pin 3, but it will be pin PB14. Here you can adjust the duty cycle and frequency. This is initial frequency, it will be the same, but initial duty cycle, let's keep it 50. It will be changed anyway. as soon as we start the code. So now I know that I need here a number between 0 and 1. Therefore, this gain block is quite suitable because here I have a gain between 0 and 100. And now I will replace this signal generator by a constant source like this, so it will be a constant value. And what I will do is that I will take this 1 as a number, as a constant. I'm going to multiply this by this gain, and I will feed this to my PWM output. So if the gain block is set to 0, now 1 times to 0 will be 0. So this will give me 0 duty cycle. If I slide it to 100, then 1 times 100 will be 100, and this will give me duty cycle of 100%. I will see that also here. So what this code will do is that I will be able to control this duty cycle, and the effect that we will see on the board is that this red LED will change its brightness. Because I will change the duty cycle, it means that I will change for how long is it on and for how long is it off. So now I have still this configuration that we've done with the serial line. I will just run the monitor and tune, and after the building process is finished, we should see that here on the board I will be able to change the brightness of this red LED. And now we have to wait until the building process is finished. It's going to take about a minute again to finish the compilation. So now it's still building. You can view the build window, and we're gonna watch what will happen. Now we can see here that it's still doing something. Until, well, in the meantime, it's let me explain you what we will do next in the next class. From next week, you will be assigned an individual project. So I will show you next week the assignment. Well, all of them will be similar in the way that you will be assigned a mathematical model that you should create in Simulink. In Simulink, you will be modeling some plant based on differential equations or a transfer function, and then you will run this model on the board and compare it with the result that you will obtain in simulation. So this is just very briefly what we will do next week, or I will assign you what you should do, and you will have 3 weeks to finish. Let me just see the schedule. I just need to refresh my browser. So this will be up to you to finish. I will give you some advices how you can do it, but if you have paid attention in the last classes, you should be able to do it on your own. So I hope that you have paid attention. You have the videos that are available. You can go back, but basically this should be your individual work. So next week on the beginning, I will assign you this work, and you'll have 3 weeks to finish. The due date will be week number 7. The compiling has almost finished in the meantime, so let me just go back with the board like that. It's almost finished. You can see here it found the port COM16, but now it's trying to initialize the comlink here, and we should see the result soon. So now here connecting to the target, and when this is done, I'll be able to, now it's successful. When this is done, I will be able to control the code from Simulink. So now you can see, okay, now it runs in external mode. I will just magnify a little bit my screen here, and I'll show you the scope. Let's move it over there. And now what I see here is the value that of the duty cycle that's coming from this block. Now you can watch that the LED here has some brightness. Let me just move it like that. If I now move the gain to, let's say, 0, as I said, my computer is a little bit slow today because of the video. So now I have moved the gain to some smaller value, like that, for example. Then here you can see I have changed the duty cycle, and now the brightness of the LED is very small. You can see here that it's barely visible, the red LED. It's because the duty cycle is small. Then the LED is on for a short period of time, and for the majority, for 90, maybe 98%, here it is off. If I now move it to the other side, like that, 100, now for the majority of time it will be on. You can see it's bright, and it's still blinking, but at least if I change it like that, so 95, let's say, it will still be blinking, but the blinking is so fast that our eyes, the camera, cannot see the blinking, but it appears like the LED is changing the brightness. So this is how the LED dimming works in principle. You blink so fast that you cannot tell the difference, but you're changing the duty cycle. And this is how it's basically done in Simulink. Of course, you can do that in C or in any other language. So what you would see on the oscilloscope is the following signal. This is my very last slide. Here, if I connect an oscilloscope, this is the real signal that we would actually measure. Well, in this case, it was a duty cycle 50%. And here the LED is on, here the LED is off, and if you change the duty cycle, basically you're changing the ratio between on and off time. So it is on and off for a different amount of time, and it appears as it is changing brightness. So, do you have any questions?
Unfortunately, Professor, none of the projects that you built, I tried all Unfortunately, Professor, none of the
Yeah.
project that
I will
you
send
built,
you
I tried.
also the
All didn't
model that
work.
I
So
have
I'll try
built
again,
right now,
maybe.
because this
It's
is built for this version of MATLAB. So maybe the problem with my models on Moodle is that they were built for the older version. I don't know, I didn't try, but I'll send you this one as well.